too many unanswered questions.
I agree. And then, of course, we have chapter 4, this black hole at the beginning of time.
Space-time singularity.
Indeed.
Suppose you had questions that have plagued the best minds for ages. Mysteries that test our comprehension of time, space, and life in general. Some of the most important questions that astrophysicists worry about at night are these ones. One by one, let's solve these mysteries. Stars, planets, and galaxies. The universe's observable matter makes up less than 5%. Others, about 25% of the cosmos is made up of dark matter, while 70% is made up of dark energy. These substances dominate it. Unlike anything we can see or touch, dark matter exists. It doesn't reflect, transmit, or absorb light. The gravitational pull it exerts on observable objects suggests its existence. Galaxies would disintegrate in the absence of dark matter. They cannot be held together by the gravitational pull of visible matter alone. By exerting a gravitational force, this invisible substance shapes the universe's structure. Because dark matter bends light due to its gravitational pull, we can detect its presence. This bending, called gravitational lensing, makes this dark material visible by acting as a cosmic magnifying glass. Dark matter's existence is confirmed by its interaction with gravity, despite the fact that humans cannot directly see it, and it is present in enormous quantities. Conversely, dark energy is considerably more elusive. The universe is expanding more quickly as a result of it. Edwin Hubble found in 1929 that the redshift in the light from distant galaxies indicated that they were moving away more quickly than those closer to them. As was previously believed, this expansion is not slowing down. Dark energy is driving it to accelerate. The majority of the universe is made up of this enigmatic force that is inherent to space and acts against gravity. Dark energy increases with the expansion of space. It seems as though this energy, which is always creating new space, is a characteristic of space rather than a physical material. No hypothesis yet completely explains the nature of dark matter and dark energy, despite the fact that we have a number of theories ranging from exotic particles to a property of space itself. This scientific frontier denotes the boundaries of our present understanding, which is naturally disheartening. These riddles serve as a reminder that we are only beginning to explore the vast cosmic ocean and show us how much more we still don't know when we venture into these unexplored cosmic realms. The greatest mysteries in our cosmos are frequently solved by the most inconspicuous components. Among these, antimatter is more than just a mystical material that appears in science fiction films. It is among the most perplexing scientific riddles. Why is there anything at all? There is an antiparticle for each particle in the universe. In charge and spin, it is completely contrary, but otherwise, it is the same. Positrons are found in electrons. There are antiprotons and protons. As matter and antimatter collide, pure energy in the form of photons is released, leaving nothing in their wake. The universe should have self-destructed moments after the Big Bang, leaving nothing but light, if this perfect symmetry had held true. However, the fact that we are here proves that didn't occur. We are able to see, feel, and inhabit matter. This raises an unavoidable query. Why does matter outnumber antimatter? This imbalance, referred to as the matter-antimatter asymmetry problem, implies that circumstances favoring the synthesis of matter slightly more than antimatter existed at the beginning of the universe. The cosmos as we know it began when one particle of matter remained unpaired for every billion pairs of particles and antiparticles that destroyed one another. A fundamental asymmetry in the laws of physics, specifically in the way the cosmos handles matter against antimatter, is implied by this tiny favoring. Despite its remarkable success, the standard model of particle physics fails to explain this asymmetry. The goal of experiments like the ALINA facility and the ALPHA experiment at CERN is to trap antihydrogen and compare its behavior to that of hydrogen. Scientists are able to investigate the fundamentals of contemporary physics by measuring the gravitational field response of antihydrogen atoms and examining their spectral lines with previously unheard-of accuracy. They are testing the fundamental symmetries of space and time, as well as the characteristics of antimatter. We don't have complete physics models yet. They fall short of providing a complete explanation for why there is something instead of nothing, why the cosmos favors matter over antimatter, and why we exist. This is only the first part of the observable cosmos, which extends 46 billion light-years in all directions. The unobservable cosmos is located beyond this cosmic border. Given the constraints of time and light, it may be infinitely larger and completely invisible. This is what might be on the other side. There could be an infinite number of galaxies in the universe, which could stretch indefinitely. An endless pattern of galaxy clusters and gaps might be created by matter repeating throughout an infinite area, mirroring the portion of space that is visible to humans. Alternatively, you could eventually return to your starting position if you travel far enough in one direction, since the cosmos might circle back on itself like a higher dimensional spherical. A universe that is both finite and borderless is suggested by this closed universe.
Galaxies are moving farther away than light can travel because of the expansion of the universe, which is accelerated by dark energy and stretches space itself. The distant reaches of the cosmos are sealed off by this expansion, which also guarantees that they will always be concealed from us. The vast, potentially endless expanse of galaxies, star systems, and other phenomena that lay beyond could be very different from the physics we are familiar with. Some of the most intriguing objects in the universe are black holes, which are places where gravity is so strong that nothing can escape. Due to infinite density and gravity, the singularity, the center of a black hole, is where the known rules of physics stop working. The event horizon, the final point of no return, is traversed on the way into a black hole. After this, all theories turn into conjecture, although general relativity implies that time and space are interchangeable. The singularity, where conventional dimensions of space and time completely collapse, is the inevitable destination of all trajectories inside this limit. Density and gravity peak in the singularity when they are thought to be limitless. Any physical stuff that dared to approach would be destroyed by the unfathomable crushing forces. The standard equations of physics collapse here. We know that all matter is compressed into an indefinitely tiny point at this core, when space-time's curvature becomes infinite. Given that black holes are only specified by three characteristics, mass, charge, and angular momentum, depicting one might appear straightforward. However, since information cannot be lost in accordance with quantum theory, the black hole information dilemma emerges. Since information flowing into a black hole seems to vanish, which is against quantum principles, this paradox represents a fundamental conflict between general relativity and quantum theory. Theoretically, exploring beyond the event horizon can result in some of the most surreal situations. According to some hypotheses, black holes might serve as portals to other regions of the universe, or perhaps other universes. This idea is sometimes represented by the image of a wormhole. Such scenarios, however, are hypothetical in nature and have not yet been supported by empirical data. Essentially, the core of a black hole continues to be a site of extreme physical circumstances and great theoretical interest. It symbolizes one of the universe's most extreme settings, when the established laws of physics are not just violated, but completely destroyed. Black holes continue to test our comprehension of the basic structure of reality as we work to comprehend the forces at work within these terrifying objects. The Big Bang, a tremendous explosion of reality as we know it, is where time, space, and matter were all formed in a single defining moment. It represents the beginning of all we know. The Big Bang, as its name suggests, was an expansion of space rather than an explosion in space. The universe was minuscule, hot, and dense at the time of this occurrence. The basic structures of stars and galaxies that we see today were laid down by the universe's stretching and cooling from this violent beginning. The Big Bang Theory, as the universe's beginning, is still unquestionably supported by the most recent discoveries made by the James Webb Space Telescope. According to the Big Bang Theory, the universe began as a singularity, or point, and has since been expanding. Particles and antiparticles produced and were swiftly destroyed as it grew, cooling from a state of unfathomable heat. The universe's temperature dropped enough during this period for quarks to combine to create protons and neutrons, which in turn gave rise to atoms. During this period, the majority of the matter in the universe, the matter that gives rise to stars, planets, and people, was formed. The cosmic microwave background radiation, a thermal residue from the time atoms first created, some 380,000 years after the Big Bang, is a significant finding that offers a glimpse into the early cosmos. With a panoramic view of the universe at its inception, this relic radiation is what's left behind from that primordial heat. Although the Big Bang Theory provides a strong account for the beginnings of the observable world, it also raises important questions. What was the Big Bang's precursor? Is our universe the only one in an endless multiverse, or is it just one of many? These queries cast doubt on our comprehension of natural principles and raise the possibility that undiscovered frameworks and theories may limit our knowledge of the universe's beginnings and ultimate destiny. We find ourselves looking back in time, as well as into space, as we continue to investigate these cosmic riddles, getting closer and closer to that initial moment of creation. However, the more we discover, the more it appears that the cosmos is keeping its secrets. The ultimate question might still be just out of grasp. Do we really think that the universe is doubting its own existence?